So hi everyone, thanks for coming. And I'm Valerii. I'm lead data scientist at FreshBooks. This is a company that develops a software product to simplify accounting for small and medium business owners. And first of all, let me introduce with my co-speakers today, Roshan, Vlad, and Zhou. And today we are going to talk about one project that we as a hybrid team of data scientists and engineers have been working on for about a year, and we achieved some significant results. Long story short, we have been able to go from mostly manual processes in machine learning model deployment to fully automated CI/CD pipelines. And as a result, our models go to prod now more than 100 times faster than before. And technically speaking, we are currently somewhere in between level 1 and level 2 in MLOps maturity, as it was defined by Google. And if you check the link below on this slide or just Google MLOps maturity and find the definition, then we can easily skip the theory behind the definition and just go straight to the few aspects of our MLOps journey. First, we wanted to talk about how we built our end-to-end machine learning pipelines in production using Kubeflow and more declarative approach. And also we wanted to talk about how it feels like working as a hybrid team on a massive initiative, such as building an ML platform. And now, let me invite Roshan to continue.
Thanks, Valerii. Let us talk about our journey in machine learning pipeline framework development. When we started streamlining our MLOps practices in our organization, we had just migrated from AWS Cloud to Google Cloud, and we were pretty new to this platform. At that point of time, we have trained and deployed our models manually using the UI button-click features of the Vertex AI platform. Moving towards the next levels of MLOps maturity, we have identified the key components required in our ML workflow, which include continuous training pipeline, model and data validation components, and metadata management component, etc. And we have built our continuous training pipeline using the Kubeflow ecosystem. This enabled us to convert each component into a Docker container that enabled portability and reproducibility while handling resource management and workload orchestration via Kubernetes. Later, we have migrated our machine learning workflow into declarative framework with CI/CD implementation, which we will be explaining later in our slides. Before that, let me discuss the design approach of developing a component in Kubeflow. Each component implements a particular step in the machine learning workflow, and it has to be reusable. Each component takes some parameters as input, and it implements some logic, and it produces some outputs. Here we have implemented the component logic as a Python function because it is easier to iterate, and also it will generate component specification file for us. As an example, I have taken the data validation component, which will decide whether we should train the model or stop its execution whenever there is an issue with the training data. As you can see on the figure on the left-hand side, this function takes 3 inputs. The first one is the project ID. This is nothing but the Google project where we want to run this component. And the second one is the expectations UTRA. Here for data validation, we use a third-party library called Great Expectations. We use this library to generate the data validation rule, and we store this in Google Cloud Storage. And in this parameter, we need to provide the URI of that particular file. And the third input parameter is BQ table. This is nothing but the BQuery table ID of the table which contains the training data. This component produces 2 output. One is the validation doc. This is nothing but an HTML doc which consists of all the validation and their results. And also it produces a variable called validation result, which consists of success or fail statuses. And based on that, we can branch out the machine learning workflow. Once we are ready with component logic as a function. Next, what we need to do is we need to load this logic as a component in pipeline.py file. If you look at the figure in the top right-hand corner, you will find we use Kubeflow's SDK's create component from function v2 package to load that particular Python function as a component in pipeline.py file. And here it takes 4 input. The first one is the function name that we have implemented the component logic. Here in our case is validate training data. The second one is base image, which is the base image of the Docker where we want to run this particular component. And the third one is packages to install, which consists of all the dependencies which we need to run this component logic smoothly. And also the fourth one is output component file, which is nothing but the path to generate the component specification file, which includes metadata, input, output specification, and the implementation logic itself. Similarly, we need to load and define all the components which is required for our continuous training pipeline. Finally, we need to define the pipeline flow. We use Kubeflow SDK's domain-specific language package for it. Here we need to define all the components and their input-output dependencies, and ultimately it will get translated to directed acyclic graph when we submit this pipeline job run in Vertex AI platform. This is how the pipeline.py file will get translated to a directed acyclic graph when we submit the continuous training pipeline job in Vertex AI. This workflow starts with fetch training data. Here we'll fetch the required training data. Next, it will execute the data validation step. If the data validation step fails, we'll be collecting and we'll be writing the metadata to a BigQuery table, and also we'll be sending a Slack notification to a dedicated channel so that the team will be aware of this failure and we can take necessary actions. And if the data validation step is successful, then we will go ahead and execute the successive step, which include pre-processing step, training step, and model validation step. If the model validation step is successful, then we will go ahead and register the model in Vertex AI registry. And later we can use this model for scoring. And finally, when the pipeline run completes successfully, then also we'll be writing the metadata to a table, and also we'll be sending Slack notifications. This picture represents the continuous training pipeline framework with Vertex AI. Here, first we need to compile the pipeline.py file, and we need to upload the compile definition along with other input files such as the training SQL file, hyperparameters, the data validation rule, etc. to Google Cloud Storage. As you can see, all these input files are stored in separate folders in Google Cloud Storage. We use Kubeflow SDK's compiler package, which will convert this pipeline.py file into a single static configuration file in which the Kubeflow pipeline service can process. This Kubeflow pipeline service will convert this static configuration file into a set of Kubernetes resource during execution. We use Airflow to trigger the cloud function which in turn submit the continuous training pipeline into Vertex AI platform. The cloud function will receive this compiled static configuration of the continuous training pipeline as an input from the Airflow DAX. And we can trigger the continuous training pipeline, we can schedule the triggering of continuous training pipeline, and also we can trigger based on the live PubSub events from the MLOps monitoring components. Next, I welcome Vlad to talk about the declarative framework. Thank you.
Thanks, Roshan. Let me try. Like this? Okay. So, if I want to deploy my machine learning in production, I need to create multiple Python scripts for the components, along with their YAML metadata files, unit tests, Docker images. I need to arrange my components into a pipeline script. Then I should submit a pull request, wait for a code review. Then I should hand over my pipeline to the MLOps team and wait for them to run their CI/CD stuff. And hopefully, my pipeline will be deployed to prod. In our case, MLOps is mostly dictated by the Kubeflow pipeline's imperative nature with its freedom and creativity. So after a developer submits their pipeline and before CI/CD system runs tests and deploys the pipeline, we should go and check if our continuous integration manifests should be updated because of their complex dependencies. And here's one concrete example for you to ponder. Say, what if a pull request contains components that are reused in multiple pipelines? We should collect all of the dependent pipelines. In the worst case, from multiple repositories. We should rebuild them, and only then we approve the pull request to be merged. So such manual work created a lot of maintainability issues for the MLOps developers, and we started thinking about the novel idea, what if we may leverage a declarative approach in the pipeline's definition, for example, such Docker Compose do or Kubernetes, and we may also automate the routine steps required for the custom components creation and pipelines. What if developer defines what to do in the pipelines instead of defining how to do it? And in the suggested framework, it means the following. Instead of defining the pipeline control flow imperatively using Kubeflow domain-specific language directly, instead of function-based components and ad hoc functions in the pipelines, we want to specify the whole pipeline's recipe by declaring its inputs, components, conditions in a YAML file. After the YAML file is ready, it gets converted into the Kubeflow pipeline's specification JSON file, which is then stored in Google Cloud Storage and submitted to Kubeflow pipelines in Vertex CI. To make this conversion, to provide this conversion, we created a new compiler class which is based on the Kubeflow SDK. This is not on the slide, but we used the same approach for the custom components creation when developers create a component class with input and output parameters and artifacts specified in the predefined method. They create unit and integration tests for the component, and also they create component YAML file with the list of requirements and how a Docker image should be named, and all of the other work is automated. YAML metadata file creation and storing in Google Cloud Storage, Docker image creation and pushing to the container registry. To demonstrate the advantages the suggested approach gives to you, we put a few formulas on the slide. Since everyone is familiar with big O notation, O, we use big E to represent the upper bound of efforts required for a developer to create any script, either imperative such as Python script or declarative such as SQL query or another YAML configuration file. And what we have found is that the original imperative approach, it requires creating 4 times more Python scripts in order to create, test, and deploy an average machine learning pipeline into production. The most important aspect of the declarative approach is our fully automated continuous integration system that we were built using GitHub Actions. On this slide, you can see a sequence of steps we run for each pull request we merge. There are 2 absolutely awesome things in our overall testing practice. Components integration tests and dependent pipelines rebuilding. For the integration test of a component, we create a separate pipeline YAML file for just the component. We specify input parameters in the file. Continuous integration system takes this file, converts it into the Kubeflow pipeline specification, and submits it to Vertex AI. And if the job is finished successfully, the integration test is accepted as passed. As for the dependent pipelines, we rebuild them. Our continuous integration system rebuilds them each time we submit an update for a component which is referenced in their pipeline YAML files. So finally, in all deployment environments, our continuous integration system automatically rebuilds components, runs unit and integration tests for them, builds pipelines changed in pull requests, and rebuilds dependent pipelines. Thank you, and I'm passing the mic to Joy. Welcome him, please.
Thank you. Thank you, Vlad. After making a deep dive into the technical topics, now let's turn our attention to the non-technical aspect of a typical big data machine learning project. It's not a big secret that you guys probably know this very well. There's a communication gap between data science and the business world. And before we started our journey to develop the fully automated machine learning platform, what we didn't realize is that such a gap could also exist in a highly technical team like us. So what we realized was that data scientists generally focus a lot on understanding business problems, and trying out new models, and trying to test out the latest technologies to solve the latest business request. They want to help business folks to tackle problems promptly. While MLOps engineers, they want to implement automation pipelines to ensure the production environment is stable to avoid accidental mistakes or untested models in the production environment. So this communication gap made us realize that collaboration can be quite challenging between cross-functional teams. Different teams, under our current structure, data scientists and MLOps engineers, they are under the same data org, but they are in the different sub-teams. Like, as you may imagine, different sub-teams have different objectives, different goals, and as well as team members from very different backgrounds. So they would use different ways of thinking and different paradigms to solve machine learning problems. So for data scientists, they want to quickly iterate. And MLOps engineers, they want to ensure there's automation in every single step in the MLOps workflow so that everything is tested thoroughly and examined before they are rolled out into production. This kind of discrepancies between teams sometimes could lead to frictions. And these frictions could lead to conflict of interest and sometimes create problems for collaboration. So in order to address this communication gap, different teams in the organization had to sit down and discuss what we could do differently. So we realized two things. The first one is we need to align our objectives. So basically, what is our ultimate goal for the team to move forward, for the hybrid team to progress? We realized that we need a fully automated machine learning platform for us to help our customers to have a better experience on the platform. At the same time, we really need to help our data scientists to leverage the latest technologies, models to quickly iterate and help the business folks to solve the urgent requests. And the second thing we realized after the discussion was we need to improve our communication channel. So basically, we need to give feedback to each other as frequently as possible. Whenever there is an issue in the production or in the workflow, we need to give feedback to each other. So the MLOps declarative framework, which was described by Vlad earlier, was spawned under this context. So this new workflow helped us to improve this communication problem and the discrepancies between these two teams. Data scientists, on one hand, they could do experiments, conduct A/B tests rather effectively. They can try the latest technologies using different Docker containers, different components within the framework. While for our MLOps engineers, they can have a much better visibilities and control into the system, and they won't complain and test the code and models again. So with this kind of new approach, we can finally address the issue we discussed earlier, and our MLOps engineers and data scientists could work together and address the tech debt, such as process management, and we can also help to manage the pipelines, components, catalogs management much better. Next, Valerii will talk about the future roadmap for our team. Thank you. Thank you, everyone.
Be quick. Okay, just as a closing remark, so we were speaking about just a few things. However, the number of challenges we are facing is a lot more, and it could easily make this project a kind of adventure. So some of them are represented here on the slide. And we are looking forward to chatting with you about any of them, as well as about any other aspects of machine learning and MLOps. So please feel free to reach out to us after the presentation, like the rest of the day or tomorrow. And we are fully open to talking with you. As usual, thanks to TMLS organizers for keeping this knowledge-sharing atmosphere that makes our community so strong. And thanks everyone for your attention. Can I invite you? We have a few minutes left, so do you have any questions to all of us?
First of all, I would like to congratulate you guys. I mean, it's very hard to implement MLOps platform. I have two questions, the ones that I have had the problems historically as well. Like when the pods fail due to some underlying hardware issues during the training, how do you guys save the state of the computation and resume the training?
So could you up the volume? Because it's...
Yeah, we have trouble hearing you.
Oh, yeah, okay.
Could you up the volume?
Test. Can you hear me clearly now?
I think it's better.
Yeah. First of all, I would like to congratulate you guys. I mean, implementing MLOps platform is a hard task to do. I have two questions. First one is, when the pods fail due to some underlying hardware issues during the training, how do you guys save the state of the computation and resume the training?
Hard to understand.
Yeah. Okay, the second one is like when the leader pod fails during the training, how do you guys handle the new leader promotion?
Sorry, it's not clear.
It's not clear, sorry.
Oh, you can't understand me?
No, something with the sound. We cannot hear.
Okay, that's fine.
That's not fine.
Yeah, we really want to understand the question. Can someone help the technical side of things? Like,
Yes, please.
sure.
Yeah, okay. Great. We can keep
And when the pods fall due to some underlying hardware issue during training, how do you save the state and resume the training?
It's about machine learning management.
Okay.
And metadata management.
The first one.
So it's about Kubernetes.
All of this.
Yeah,
Kubernetes. Like Kubernetes.
can you answer it?
Yeah, sure, go ahead.
You can answer it. No, not I. Can answer. Can answer. Yeah, can you answer? I don't know.
Yeah. Okay. If you check, you like first read the question and read the question first.
Maybe. So you read the question, please.
So yeah. Can you hear me? So the first question is, when the pods fail due to some underlying hardware issues during training, how do you save the state and resume the training? This is like solved automatically by Kubeflow. It's Kubeflow pipelines itself. So it saves its state, and each time we rerun the pipeline, the components that were not like finished, they start like working again. But you mean like maybe data? How do we like continue? Like, yeah, okay, yeah. So each component runs the isolated part of work of the whole pipeline. So if some components are fails, so they may start like their work from the beginning after we restart the whole pipeline. Yeah. And the second question was like, when the leader fails during the training, how do you handle the leader promotion? What is it? Why?
Your question.
Leader. Like leader, you mean like leader mechanism, like the whole framework, or it's like a person, you mean? Leader pod. Yeah. Again, yeah. This is why we use this is why we decided to use Kubeflow pipelines, because they do it automatically. Yeah. We don't care about it. Yes. Yes. Sure.
Pipeline with how you incorporate metadata into. Is it possible?
Yeah, for sure.
More explanation.
Yep. Yeah. Okay. So the slide with the pipeline and metadata. Can we go back to it?
Can we do have the?
Is there more?
Okay. Can we bring one slide back?
We need to go back to the previous slide.
Which one? Which one exactly?
The one with metadata.
Metadata.
Sorry?
Is it your slide?
No, not this one. No. Oh, thank you.
So the question is, as I guess it correctly, can we elaborate a little bit about the pipeline and metadata, right? Like how does it work? This one? The next one? Before or next? Try version. The next one, then that. This one?
This one? Okay, what was the question?
Yeah, and the question?
Yes.
A.
Okay, so basically this is a component which will get all the metadata about this pipeline, continuous training pipeline. For example, the framework that we are using, the BigQuery training data URI. So all those data we will be writing to a BigQuery table, so that later we will have a reference of the pipeline run. So Vertex A has a metadata management system readily available, but we use BigQuery metadata system just for simplicity purpose, because the others is a little bit complex for our workflow. That's why we are writing the metadata to a table. Yes, that's just for our future reference about the training pipeline runs. Sorry? We can also analyze as well. Sorry? Not in the pipeline process, yes. Right now, the analysis process is not there in the current pipeline, yes. Problem.
Yeah. Thank you. It's time.